When dealing with a 208Y/120-volt, three-phase pad-mounted transformer, several key grounding and conductor requirements must be met to ensure safety and proper operation of the electrical system. The secondary of the transformer is grounded, and the transformer is locally grounded using ground rods and a buried bare copper grounding ring. A ground wire, sized according to National Electrical Code, or NEC Table 250.66, must be included with the service entrance conductors. This ground wire provides a continuous grounding path from the transformer ground to the panelboard ground bus. The grounded conductor, also known as the neutral, is also required and should be full-sized. There are several reasons why a full-sized neutral conductor is essential. Firstly, because the 208Y/120-volt transformer secondary is grounded, the neutral conductor acts as the return path for unbalanced loads. Secondly, the neutral conductor is used to establish the center point for the 120-volt circuits. Thirdly, the neutral conductor provides a return path for ground currents under fault conditions. The panelboard ground bus should be connected to the local ground rod via a ground rod electrode. To summarize, both the ground wire, sized per NEC Table 250.66, and a full-size grounded conductor, that is the neutral, are required to properly ground the service entrance and ensure safe operation of the electrical system. The ground wire ensures a dedicated low-impedance path for fault currents back to the source, allowing overcurrent protective devices to operate quickly and clear the fault. The full-sized neutral handles unbalanced loads and provides a stable reference point for the 120-volt circuits derived from the 208Y/120-volt system. Let's delve deeper into the specific requirements and considerations for each of these components. Starting with the ground wire, its purpose is to provide a low impedance path for fault current to return to the source, which is the transformer in this case. The size of this ground wire is determined by NEC Table 250.66, which bases the size on the size of the service entrance conductors. It is crucial to consult this table to ensure that the ground wire is adequately sized to handle potential fault currents. Using an undersized ground wire can create a safety hazard by limiting the flow of fault current and potentially delaying the operation of overcurrent protective devices like circuit breakers or fuses. This delay can increase the risk of electrical shock or fire. Now let's consider the grounded conductor, or neutral. As mentioned earlier, the neutral serves multiple purposes in a 208Y/120-volt system. Firstly, it provides a return path for unbalanced loads. In a three-phase system, the loads on each phase are rarely perfectly balanced. This means that the current flowing in each phase is not equal. The neutral conductor carries the difference in current between the phases, allowing the system to function properly even with unbalanced loads. Without a neutral conductor, unbalanced loads would cause voltage imbalances and potentially damage equipment. Secondly, the neutral conductor establishes the center point for the 120-volt circuits. In a 208Y/120-volt system, the voltage between each phase and neutral is 120 volts. This allows for the use of standard 120-volt appliances and equipment. The neutral conductor provides a stable reference point for these 120-volt circuits, ensuring that the voltage remains within acceptable limits. Thirdly, the neutral conductor provides a return path for ground currents under fault conditions. In the event of a ground fault, where a phase conductor comes into contact with a grounded surface, the fault current will flow through the ground wire and the neutral conductor back to the source. The neutral conductor helps to facilitate the flow of this fault current, allowing overcurrent protective devices to operate and clear the fault. Given these important functions, it is essential that the neutral conductor be full-sized. Reducing the size of the neutral conductor can lead to several problems, including voltage drops, overheating, and increased impedance to fault currents. A reduced size neutral may not be able to adequately handle unbalanced loads, leading to voltage imbalances and potential equipment damage. It may also overheat due to the increased current density, creating a fire hazard. Furthermore, a reduced size neutral will increase the impedance of the fault current path, potentially delaying the operation of overcurrent protective devices. Now let's turn our attention to the panel board grounding. The panel board ground bus should be connected to the local ground rod via a ground rod electrode. This connection provides a path for fault currents to flow to ground, helping to protect personnel and equipment from electrical shock. The ground rod electrode should be installed in accordance with NEC requirements, which specify the size, material, and installation depth of the ground rod. The connection between the ground bus and the ground rod should be made with a listed grounding connector. It is important to note that the ground rod is not the primary path for fault current to return to the source. The primary path is the ground wire that runs between the transformer ground and the panelboard ground bus. The ground rod provides a supplemental grounding path and helps to dissipate static electricity and other unwanted electrical noise. In addition to the ground wire, neutral conductor, and ground rod, there are other important grounding considerations for a 208Y/120 volt system. Firstly, all metallic enclosures such as panel boards, junction boxes, and conduit should be properly grounded. This helps to prevent electrical shock in the event of a fault. Secondly, all equipment grounding conductors should be properly sized and connected. Equipment grounding conductors are used to ground non-current carrying metallic parts of equipment, such as motor frames and appliance housings. Thirdly, surge protection devices should be installed to protect sensitive electronic equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching transients, and other electrical disturbances. Surge protection devices divert the surge current to ground, protecting the equipment from damage. In summary, grounding is a critical aspect of electrical safety and proper system operation. In a 208Y/120 volt, three-phase system, it is essential to include a ground wire sized according to NEC Table 250.66 and a full-size neutral conductor. The panelboard ground bus should be connected to the local ground rod via a ground rod electrode. By following these grounding requirements, you can help to ensure the safety and reliability of the electrical system. Now, let's consider some additional factors that can affect the grounding of a 208Y/120 volt system. Soil conditions can play a significant role in the effectiveness of the grounding system. Soil resistivity, which is a measure of how well the soil conducts electricity, can vary widely depending on the type of soil, its moisture content, and its temperature. High soil resistivity can make it difficult to establish a good ground connection, potentially compromising the effectiveness of the grounding system. In areas with high soil resistivity, it may be necessary to install multiple ground rods or use other grounding techniques to achieve an acceptable ground resistance. Another factor to consider is the presence of underground utilities. Before installing ground rods, it is essential to locate any underground utilities, such as gas lines, water lines, and communication cables. Installing a ground rod too close to an underground utility can create a safety hazard and potentially damage the utility. It is also important to consider the potential for corrosion of grounding electrodes and conductors. Over time, grounding electrodes and conductors can corrode, reducing their effectiveness. To minimize corrosion, it is important to use corrosion-resistant materials such as copper or stainless steel. It is also important to periodically inspect the grounding system for signs of corrosion and to replace any corroded components. The distance between the transformer and the panelboard can also affect the grounding system. A longer distance between the transformer and the panelboard will increase the impedance of the grounding conductors, potentially reducing their effectiveness. To minimize the impact of distance, it is important to use adequately sized grounding conductors and to minimize the length of the grounding conductors. Proper bonding is also essential for effective grounding. Bonding is the process of connecting all metallic parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between different parts of the system, reducing the risk of electrical shock. All metallic enclosures, conduits, and equipment should be properly bonded together using listed bonding connectors. Regular inspections and testing are essential to ensure the continued effectiveness of the grounding system. Ground resistance testing should be performed periodically to verify that the ground resistance is within acceptable limits. Visual inspections should be performed to check for signs of corrosion, damage, or loose connections. Any problems identified during inspections or testing should be promptly corrected. In addition to the NEC requirements, there may be local codes or regulations that govern the grounding of electrical systems. It is important to consult with local authorities to ensure that the grounding system complies with all applicable requirements. Grounding is not a one-size-fits-all solution. The specific grounding requirements for a 208Y/120 volt system will depend on a variety of factors, including the size of the system, the type of load served, the soil conditions, and the local codes and regulations. It is important to carefully consider all of these factors when designing and installing a grounding system. A qualified electrical engineer or contractor should be consulted to ensure that the grounding system is properly designed and installed. Proper grounding is essential for electrical safety. A properly grounded electrical system will help to protect people from electrical shock, prevent damage to equipment, and reduce the risk of fire. It is important to take grounding seriously and to ensure that the grounding system is properly designed, installed, and maintained. Furthermore, the selection of appropriate overcurrent protection devices, such as circuit breakers and fuses, is crucial for ensuring the safety and reliability of the electrical system. These devices are designed to interrupt the flow of current in the event of an overload or short circuit, protecting equipment and preventing fires. The size and type of overcurrent protection devices must be carefully selected based on the ampacity of the conductors they protect and the characteristics of the loads they serve. In addition to providing overcurrent protection, ground fault circuit interrupters, or GFCIs, are also essential for protecting people from electrical shock. GFCIs are designed to detect ground faults, which occur when current leaks from a conductor to ground. When a ground fault is detected, the GFCI quickly interrupts the flow of current, preventing electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Installation of surge protective devices, or SPDs, is also important for protecting sensitive electronic equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching transients, and other electrical disturbances. SPD divert the surge current to ground, protecting the equipment from damage. SPD are available in a variety of types and sizes, and the appropriate type of SPD should be selected based on the specific needs of the application. Regular maintenance and testing of electrical equipment are also essential for ensuring the safety and reliability of the electrical system. Electrical equipment should be inspected regularly for signs of damage, wear, or corrosion. Electrical connections should be checked to ensure that they are tight and secure. Overcurrent protection devices should be tested periodically to verify that they are functioning properly. Grounding systems should be inspected and tested to ensure that they are providing adequate protection. Any problems identified during maintenance and testing should be promptly corrected. Electrical safety training is also essential for all personnel who work with or around electrical equipment. Electrical safety training should cover topics such as electrical hazards, safe work practices, lockout/tagout procedures, and the proper use of personal protective equipment. Personnel who receive electrical safety training will be better equipped to identify and avoid electrical hazards, reducing the risk of accidents and injuries. In addition to these safety measures, it is also important to follow all applicable codes and standards. The NEC provides comprehensive requirements for the design, installation, and maintenance of electrical systems. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. Local codes and regulations may also impose additional requirements. It is important to consult with local authorities to ensure that the electrical system complies with all applicable requirements. Electrical safety is a shared responsibility. Everyone who works with or around electrical equipment has a responsibility to follow safe work practices and to report any electrical hazards that they identify. By working together, we can create a safe electrical environment for ourselves and for others. The principles discussed here apply broadly to many electrical installations and serve as a foundation for understanding and implementing safe electrical practices. Remember to always consult the latest edition of the NEC and local codes for specific requirements, and to engage qualified professionals for design, installation, and maintenance of electrical systems.